Hello, this is part 2 of chapter 1 lecture where we are going to discuss about scientific measurement and what type of units we use for different types of measurements for matter, and we are going to discuss a little bit about temperature and derived units such as volume and density towards the end of this lecture. So let's briefly discuss why there is a need for scientific measurement. So whenever you measure anything, you need to represent in a scientific data, which should include both the number and the unit followed by it. So a number has no meaning without followed it up with a unit. Let's say there is you're trying to calculate how many calories you are eating in a day. So you need to, let's say you find a website where you can enter how many carbohydrates you're eating, how much of fat is you're eating, how much of protein you are eating. So without you put up the correct unit next to, let's say you have taken for your breakfast 50 carbohydrates, what it should understand, have you taken 50 milligrams of carbohydrates or 50 grams of carbohydrates or 50 pounds of carbohydrate, right? So without a unit, a number makes no sense. So scientific measurement is a combination of both the measured number as well as the unit followed with it. It's called scientific measurement. And we use different apparatus for different purposes. Sometimes you would use a scale to measure a particular weight, or if at all you have a liquid matter, you would use one of these burette, a burette or a volumetric flask or a graduate cylinder or another volumetric flask to measure anything that you have at your hand. And when it comes to scientific measurements, we need to specifically say it here because in the USA, we use a different measurements than the scientific world. In the USA, we use the measurement called English system, where English system contains units such as miles, pounds, gallons, quarts, or ounces, all of these. However, the scientific world and the rest of the world would use a system called SI system, or in more general words, metric system. So metric system contains units such as milliliter, grams, kilograms, liters, kilometers, these centimeters, these types of units. So scientific study, science classes, you're always going to use these SI units, or in common words, metric units. Let's see what are those. Right. So these are some of the examples of the quantities or type of quantities that you would use to measure different matter. Sometimes if you are going to measure length, so for each different type of measurement, there is a particular base unit. So it is easy to understand or easy to name, or you can think of it in terms of increments of those base unit. So length has a base unit of meter, and the mass has a base unit of, well, mass has a base unit of grams. Here we name it as kilogram, and time has a base unit of seconds. So please correct about the mass. Mass has a base unit of gram, and we think of in the gram. So when you say kg, it is actually kilogram. So it is not a base unit. There is a typo here. And there are other less popular units that you can still measure, but we don't use a lot in chemistry, such as electric current, which measured in amperes, or amount of substance, which measured in moles, and luminous intensity, which measured in candela. Temperature we do use, and temperature, the base unit is a Kelvin. So we are going to discuss all of these. So here is a table that you can use to symbolize the magnitude of a base unit. In the previous slide, I said length has a base unit of meter, and mass has a base unit of gram. So in comparison to these base units, if you use these prefixes of such as tera, giga, mega, kilo, deci, centi, milli, micro, nano, and pico, you can imagine if that new unit is bigger than a gram or smaller than a gram. Okay, so here you have, let's say, kilo. Kilo means 1,000 times of a base unit. So see it here, it is multiplied with 1,000. And a mega means 1,000,000 times of a base unit. So it is multiplied with 10 to the power of 6. A giga means 1,000,000,000th times of a base unit. So it is multiplied with 10 to the base of 10. A tera means 1,000,000,000,000 times of a base unit. So it is multiplied with 10 to the exponent of 12. So similarly, when you see a prefix a deci in front of a base unit, you have to think that it is only 1/10th of that base unit quantity. So centi is 1/100, milli is, 1/1000, and micro is 1/millionth, and nano is 1/billionth of a base unit, and pico is 1/trillionth of a base unit. So that's why you need base unit, and you add these prefixes to the base unit so that you could easily imagine if the new unit, such as, let's say, if I say megagram. So you know that gram is the base unit of mass. So if I say these many megagrams, so you can imagine that, oh, that number is much larger because mega is million times of a gram. So you can imagine that it's a bigger quantity. That's how we use this. All right, let's discuss what are the definition of mass. I've been saying mass, right, a couple times in this lecture. So a mass is measure of how much of matter present in an object or sample. So, but in comparison to that, weight is basically as a result of the gravitational force a mass feels. That is what we call weight. So mass is something that you can always rely on, because think of me here on earth. I weigh a lot of weight because I have, let me restart. So a mass, for example, if you think of me, I am made up of certain number of carbons, oxygens, hydrogens, and rest of the elements, right? So these elements I wouldn't lose if I'm here on Earth, or if I'm on Moon or Mars or Venus or any other planet. I wouldn't lose whatever the mass I already have, because it is the matter that I already possess. I wouldn't lose these. However, I'm going to weigh differently on different planet because there is a different gravitational force that planet has. So it pulls me back to that planet with a different force. So I would weigh differently on Earth, to the Moon, to the Mars. That's the difference between mass and weight. So again, we discussed a base unit. So as a base unit of mass is, and it keeps saying kilogram, but I want to say it a gram because it is more accurate. The SI base unit of mass, I would say, is the gram, so that when you say kilogram, you can imagine that, oh, 1,000 times of the gram. So what are the units that we use to measure the masses? Our universe or any matter that you experience is made up of elements, and elements has certain amount of mass, so that mass you have to measure. So those measurements, that we call it as atomic mass unit. So atomic mass unit has the weight of 1.660537 10 to the power of -24 gram. It's a really small quantity, but we are talking about only one tiny element atomic mass unit. Different elements has different number of atomic mass units. Even still, that number is much more smaller. So we are going to discuss how to measure these really tiny elements in a bunch in next couple chapters. But this number is something that you are going to remember because we are going to use this number a lot in this class. The atomic mass unit is 1.66 times 10 to the power of negative 24 grams. Let's see what else we have. So far we have been discussing scientific measurement, and we discussed why there is a need for measurement number as well as unit to follow it up with, so that those numbers are considered as scientific numbers. So now we are going to discuss temperature. So temperature we use to measure how hot or cold an object is. So in scientific measurements, I already told you that in a chart a couple slides ago, the base unit that we use is the Kelvin. So here I'm going to introduce you both common scientific reading, common temperature reading, as well as the base scientific reading. So one of the reading is Celsius degrees here. So Celsius degrees, if you want to have some reference, for example, water has 0 degrees Celsius and 100 degrees boiling point. However, the most popular or accurate reading to use in scientific measurements is a Kelvin. So Kelvin has a scale of from 0 degrees Kelvin to 0 degrees Kelvin, which is, we call it as absolute temperature, because beyond that you cannot reach any further lowest temperature. So there's a conversion between Celsius degrees to Kelvin temperature, because Kelvin, you can define that relationship as Kelvin temperature is equal to degree of Celsius temperature plus 273. So which means from that equation you can tell that if the water freezes at 0 degrees Celsius, it should freeze at 273 Kelvin temperature. Or if water boils at 100 degrees Celsius, water should boil at 373 Kelvin. That is how you would use that equation. Okay, let's work on a problem. All right. So the problem here says the normal human body temperature can range over the course of a day from about 36 degrees Celsius in the early morning to about 37 degrees Celsius in the afternoon. In general, temperature slowly rises as day goes by, because we get tired, we will be active, so we need some rest. It is body's way of saying you need some rest by the evening. So express these two temperatures and a range that they span using Kelvin scale. Let's look into it. So because it is saying, you got the temperature in Celsius and you need to express them in Kelvin. So your plan should be finding an equation that correlates the Celsius and Kelvin temperature. In the previous slide, we discussed the relationship between Kelvin and Celsius is that Celsius plus 273 is equal to Kelvin temperature. So these numbers here, you can simply say 273 or 273.15. Those two numbers are correct. Not having 0.15 is totally fine, because it is not going to make any significant differences in your answer. So a lot of times you just get by using 273. So it is not an issue. So I expect you to, whenever I show you a problem, I expect you to pause the video, practice on it, and then check this answer. So it is easy now. So you can easily plug in those 36 and 37 and find the temperature. So the new Kelvin temperatures is 309 and 310. So the question asked is, in what range they span? It is same as the Celsius range. 36 to 37 has only 1 degree Celsius range. So that 310 to 309 has 1 Kelvin range. So the magnitude of difference between temperatures is same, because of the formula is you're just adding the same 273 number to both 36 and 37 degrees Celsius. So this is one thing to keep in mind as we are going to discuss about the other type of, or the third type of temperature, Fahrenheit. So in USA, here we use Fahrenheit temperature against to Celsius temperature in daily life, but Fahrenheit temperature is not used in scientific measurements, but just because we are using it outside, and sometimes you might need to know how to convert Fahrenheit to Celsius or Celsius to Fahrenheit, and we're just going to discuss what is that formula is if at all you require to convert Fahrenheit to Celsius. So we already discussed that water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. And we know that here in USA, water freezes at 32 degrees Fahrenheit and water boils at 212 degrees Fahrenheit. And now if you compare the difference between Celsius from 0 to 100, the difference between melting and boiling point of Celsius range is 100, whereas the difference between freezing point in Fahrenheit to boiling point in Fahrenheit is much more larger than 100. So because there is a huge range span between these two, we can say that the range of Fahrenheit is about 9/5 times of the Celsius range. Then you can propose an equation to convert Fahrenheit temperature to Celsius temperature. So to convert any Fahrenheit temperature to Celsius temperature, you can simply multiply 9/5 with the temperature that you have at your hand on 0 degrees Celsius and add plus 32, then you will get the new Fahrenheit temperature. So that is how you would convert that is how you would convert Celsius degrees to Fahrenheit temperature. Now let's look into a problem. So problem says a body temperature above 39 degrees Celsius constitutes a higher fever. Convert this temperature into the Fahrenheit scale. Okay, so we just saw the relationship between Fahrenheit and Celsius, so we know what equation to use. So you were asked to identify Fahrenheit temperature, so simply we multiply 39 degrees with 9/5 and add 32 to it to get to the new Fahrenheit temperature. So now plug in those numbers, you should be getting 102. So that is definitely high fever. So if it takes 39 degrees Celsius or 102 degrees Fahrenheit, it considered both as high fevers. Not healthy. All right. So far we have been discussing about scientific measurements, and mostly we discussed so far the measured units. What is measured unit is when you measure the length, you measure it in meters, a base unit. When you measure the mass, you measure it in grams, the base unit. What if you need to measure a different property? For example, matter has a unique property called density. What is the definition of the matter again? Matter is anything that occupies mass and volume, right? So if something is occupying mass and volume, it has to have some type of relationship between its mass and volume, and actually it does. Density is a unique property to each component. For example, water has the density of 1, whereas cooking oil has the density of less than 1. That's why whenever you mix a cooking oil with water, cooking oil always floats over water because cooking oil has less density than water. So density is a property, an intrinsic property of matter. So it calculated based on how much of mass it currently has and how much of volume it is occupying. So it seems like there are two units going into the density, which is mass and volume. So that's why there are two units going into it. We are calling density as a derived unit. Is it making sense? Right? We're calling density as a derived unit because it is a combination of two units, both mass and volume. So mass, we already use the unit meters as a base unit. Let's see if we can write. Mass base unit is, grams, and volume we haven't discussed directly what is the volume based unit is. So volume, I should say, is calculated by calculating the length, width, and height of a sample. It is not clear there. Let me write it again. Length, width, and height. You need all these three things. So if you could calculate those, for example, look at this sample that you have here. Here you have three different dimensions of, let me get my highlighter. You have the height, width, and length of these three different of these samples. So using these three parameters, you could identify the volume. So what are you using to measure these length, width, and height is you are using unit called base unit called meters. So meter is in larger term than grams. So what you can do is you could propose the density as in similar magnitudes of both mass and volume. So later is as a result of length in meters and width in meters and height in meters. So length, width, and height. So you can combinedly say length, oh, excuse me. Let me just correct myself. I should be just saying this one has volume. When you calculate volume, you need length, width, and height information. And let's say you measured all of them in its base unit of meter. So they were in meter, meter, meter. So you can say that meter cube. Okay. So to keep them in same magnitude, because you were saying meters, mass, it would be kilogram because it's in the same magnitude for the mass. So to get the density, you can say like density is mass over volume. So you can say like kilogram over meter cube. That will be one type of common units for the density. Or to have the same magnitude but in smaller units, you can say like grams over centimeter cube. They were in the similar magnitude. So we're going to look into different types of units in the next slide. Let's clear this and go to next slide. Right. So as we discussed, density is a ratio of mass over volume. So what are the units of this is derived units of density in SI system is kilograms over meter cube. However, not always you will have a large quantity where you can measure it in meters reasonably and kilograms reasonably. So you could have for different type of matter, different types of units. For example, for solids, solids are dense matter. So it wouldn't be having lots of volume to measure because they were dense. Maybe they will have small quantity. This is, for example, penny here is a solid. See how much of length it has, right? Small length. So it would be hard to measure it in meters. So you would reasonably measure them in centimeter cubes. And let's say you have grams, which, reasonable quantity for the centimeters. If you're measuring volume in centimeters, you should measure mass in grams. Let's say you have liquids. Liquids, you measure the volume in milliliters because it is the most convenient way to measure, because you pour them in a graduated cylinder or you use a burette or a volumetric flask to measure. So volume of liquids measured in milliliters and mass is measured in grams. Whereas for gases, gases are molecules that are spread out a lot. So it is hard to measure them in meters because you cannot really use a scale like in gases. So you could measure them in terms of liters of gases based on what container it is occupied. And because they have really low density, because gas molecules are far apart, they wouldn't weigh much. That's why you use the mass base unit as a gram. So there are different types of units you have to use for density, and it is a little bit confusing, but you get used to it. It is, based on explanation of what type of matter you have at hand. Do you have a thick density matter solid, or labile liquid that is hard to measure using a scale, or gases that are spread out? Okay. Let's see what we got here. The last slide here, we are going to end this lecture with working on a problem. So let's see, this problem says, ice cubes float in a glass of water because solid water is less dense than the liquid water, okay? Calculate the density of ice given that at 0 degrees Celsius, a cube that is 2.0 centimeters on each side has a mass of 7.36 grams. Let's see what we can do with those data. So part B asks, determine the volume occupied by 23 grams of ice at 0 degrees Celsius. Okay, let's look into the data. So what you got here is, you were told what is the length, width, and height of the ice cube, and you were told how much of mass that ice cube weighs, and you were asked to calculate the density. And you just saw that in the previous slide. What is the relationship between density, mass, and volume? We just said that density and mass are related to each other for the volume as density is equal to mass over volume. Okay, so and I also told you that volume you can calculate by multiplying the length, width, and height of a sample. So you need to identify volume, and luckily you were directly given the mass as 7.36. So let's find out what is the volume is. Volume, you were told that it is 2 centimeters on each side. So you're going to multiply 2.03 times, as in the case of identifying the volume by multiplying the length, width, and height of the sample. So it will be 8.0. Because you are using centimeter each time, it will be centimeter cube, right? So to identify the density, use the density, excuse me. And you see mass over volume. So you already know the mass, which is 7.36 grams over the volume of 8.0 centimeter cube. So if you calculate by yourself, you should be getting a value of 0.92 grams over centimeter cube. Let's look into another problem. The second problem, B. So it said that determine the volume occupied by 23 grams of ice at 0 degrees Celsius. So in this case, it is asking what is the volume occupied by it, and it gave different mass, which is 23 grams. Let's see. In this case, you are asked to identify volume. So, but what is the rearranged equation? Because you already know the relationship between density, mass, and volume in one equation, you could use that to rearrange the equation to have volume on one side and plug in the density value you just identified in the problem 1 and use the mass value of 23 grams to identify the volume. So density is equal to mass over volume. Let's separate volume to one side by multiplying both sides with volume. You do that, you can cancel volumes. Now you have volume times density is equal to mass. So to have volume on one side, you can divide density on both sides, And if you do that, you will have density cancelled. So you can say like volume is equal to mass over density. Now that you know what is the given mass is 23 grams and density as 0.92, you can plug in those numbers. So 23 grams over 0.92 grams over centimeter cube. So you will have the answer as 25 centimeter cubes. So an ice that weighs 23 grams occupies 25 centimeter cubes of volume because it has larger volume and lower mass. Okay. Let me clear that in so that you could read this. All right, that's all for this part of the chapter. I'll see you guys again in the next part.